Hi, so this section is, in the last section of chapter 5, is what we call about the central limit theorem. And the central limit theorem is a pretty big, um, a pretty big theorem in statistics. It's one of the, if not the most important theorem in statistics. All right, and so what I'm going to do is I think I'm going to break this up into a couple videos just introducing the central limit theorem and what it's about, because I think that deserves its own video. And then I'm going to explain more in depth, like some problems and the actual statistical problems that we do involving the central limit theorem. Okay, so the first thing we need to talk about really about the central limit theorem is a sampling distribution. And a sampling distribution is a probability distribution of a sample statistic that is formed when samples of size n are repeatedly taken from a population. So what we're going to do, this is kind of abstract to think about, but we have a population and we're going to keep taking samples from that population repeatedly. And in those samples, what we're going to do is we're going to take a statistic. And specifically, the statistic that we are going to be concerned with is the sample mean. It doesn't have to be the sample mean. And if you study statistics more, you'll realize you can do this with any sample mean or with any sample statistic. But we're going to talk about the sample mean. So specifically, we're going to talk about the sampling distribution of sample, that's an S, sample means. We're going to talk about the sampling distribution of sample means. So let's say this is a population. And what we're going to do is I'm going to get a sample from my population, and I'm going to get the mean of that sample. Now, the population has a mean of mu. And that's always going to stay the same. But depending on what sample you get, you're going to get different means. Like if I got 5 people's heights, let's say, and found their average height at Chesterton High School, and then I got a different 5 people's heights and found their average height, there's no reason why those averages should be the same. They might be close to each other, but they're not going to be exactly the same, or it's very unlikely they'd be exactly the same. So we're going to get the mean of the first sample. We're going to get a second sample. We're going to get the mean of the second sample. And so I have a subscript 1 for the first sample, subscript 2 for the second sample. And we keep doing this. So we get a third sample, get the mean. These samples could overlap, by the way. And we do this again and again and again and again. And eventually, all these x bars get us what's called the sampling distribution of sample means. And it turns out this sampling distribution has properties. The first property is the mean of the sample means, which is pretty abstract. So if I have all of these x bars, I get all these x bars, so I stopped at 5, but I'll have a bunch of them, right? Let's say I have thousands of x bars. If I take the mean of all of those means, I will get the population mean mu. The mean of the sample means, which we denote with a mu sub x bar, is equal to the mean of the population. And notice my notation here. Mu is the mean of my population, so this is the population mean. That's what we've always used for the population mean. But this is the mean of sample means. So this is the mean of the sampling distribution. Now, they're equal to each other. They're the same number, but the notation, mu sub x bar and mu, mean, no pun intended, two different things. Excuse me. Okay, next we're going to talk about standard deviation. Now, standard deviation does not stay the same. The standard deviation of the sample means is equal to the standard deviation of the population divided by the square root of n. And this is also called the standard error of the mean. So the standard deviation, or the standard error of the mean, which is sigma sub x bar. So once again, this is the standard error, or you can even call it the standard deviation of the sample means. Standard error of the mean. This is the population standard deviation. So these are not equal to each other. It's actually a function of the square root of n. And if you think about it, if our sample size, because n is the sample size, I'll just point all these out. So if my standard deviation, or if my sample size increases, I'm dividing by a larger number. And if I'm dividing by a larger number, then that means my population standard deviation is going to be divided, which is always the same, is going to be divided by a larger number, and therefore my standard error goes down. So basically, as my sample size increases, my error decreases, which makes sense because if your sample size is large, then you are getting more information from your population, and therefore your overall standard deviation or standard error of the mean is going to decrease. All right, so this is about the center. This is what we call about the center. This is the first thing. This is the spread. And the third thing is the shape, which brings us to the central limit theorem. And basically, the central limit theorem says if your sample size is large enough, and we say if n is greater than or equal to 30, then the sampling distribution of sample means is always approximately normally distributed. And 30 is kind of a line in the sand. It doesn't have to be 30, but for our purposes, we're going to use the sample size of 30. So if your sample size is greater than or equal to 30, you can pretty much say that your sampling distribution of sample means is approximately normal. So what this means, again with the puns, so let's say we have a population distribution that just looks really weird. So I'll put an X here, and let's say, I don't know, my mean is mu, and this is my standard deviation. Well, it turns out that, and I just drew a really weird population. It turns out that as long as your sample size is greater than or equal to 30, your mu sub x bar is equal to your mean, sigma sub x bar, small, but do you see the bell shape? It's approximately normal. And that's very important. So basically, it doesn't matter what your sample is, or your population is. If your population is really weird looking, it could be bimodal, it could be skewed, it could be whatever, you always get a normal distribution every time. This happens every time your sample size is large enough. Okay. Now, if you already have a normal distribution, you won't get you'll still get a normal distribution, but how did I draw this? It's skinnier, right? And that's because the standard deviation decreased. Remember, your standard deviation is sigma sub x bar. Your standard error is sigma sub x bar. And that is going to go down as your sample size increases. So even though you already have a normal distribution, even if you know your population is normally distributed, it's still worth it to get a larger sample size, because what the larger sample size does is it reduces the variance among the sampling distribution of sample means. Okay, so let me give you a little bit of, I have this applet here to kind of show you what happens. So what this applet does is this applet is going to calculate the mean of a sample of size 2, and it's going to calculate the mean of a sample of size 25. And let's just start with a normal distribution. So if it's normally distributed, it's going to get 2 data points, and then the blue dot is the mean, and then it's going to get 25 data points, which is going to take a little bit longer, and it's going to get the mean of these 25 data points. Okay, so we did the simulation one time for each sample size. We did it here and here, and we can keep doing this. So again, we do this over and over again. There's one, and the second one for the sample size of 25. By the way, it bothers me that they use capital N's here because it should be lowercase n's because they're sample sizes. And we have the second one. So we can do this over and over and over again. And let's do it 10,000 times. I just hit the 10,000 button. And notice that my original population is very spread out. my sampling distribution of means n equals 2 is actually a little bit closer together, and when I have n equals 25, it's very close together. And that's because my standard deviation decreased as my sample size increased, and we still maintained a normal distribution. Again, this happens every time. And if I look, my original, I don't know if you can see this, but my original standard deviation is 5 for the population. And remember that standard deviation, the standard error, let's go back to the notes here, the standard error is sigma over the square root of n. Well, if my original standard deviation is 5, and I divide by the square root of 25, because my sample size was 25, that's 5 over 5, which is 1. And you'll see in the simulation that my standard deviation is about 1 for n equals 25. And that's what it should be, because my standard deviation got decreased. The spread of the data is closer together for a larger sample size. Okay, so let's do another one. Let's do a skewed distribution. So is this normal? Absolutely not. Let's do this 10,000 times. So notice that if my sample size is 2, it's still pretty skewed. I wouldn't call this normal at all. But once my sample size is 25, and remember, if our sample size is greater than 30, it won't let me do a sample size greater than 30. But if I do a sample size greater than 30, I should get something that's approximately normal. And even at a sample size of 25, which is pretty close to 30, I get something that's approximately normal. So this happens every time. You can even do like a custom distribution, so it'll let you like draw your own thing. Like I'll draw that, and I'll do this, and look, you know, at sample size of 2, not really, but at sample size of 25, it almost looks perfectly symmetric again. And it always happens. This is the beauty of the central limit theorem. And what this does is allows us to apply our normal distribution chart to basically any data set that exists. So as long as we're talking about the sample mean and the means, we can basically predict what averages are of entire populations using the central limit theorem, as long as our sample size is large enough, which is pretty cool. All right, so basically to summarize, there's 3 things that you should take away from the central limit theorem, and that is that 1, the center of the sampling distribution compared to the original population doesn't change, right? No change. Okay? The spread decreases, right? The spread decreases as n increases. And then finally, the shape becomes more normal as n increases. Okay, so those are basically the 3 takeaways from the central limit theorem. And again, we're taking a bunch of samples, or we're taking samples, and we're using that sample size we're using that sample from the population. It turns out that those sample means, those distribution of sample means, has these 3 characteristics. The center doesn't change, the spread decreases as n decreases, and the shape becomes more normal. All right, so the next part of the video, I'll complete the notes, and we'll actually do a few problems that are related to the central limit theorem.